So this next one is here. Something must be added here. Okay, I'm going to show you what the issue is. So, and then we'll have the final form of this. Okay. So let's consider the following. Okay, please pay attention to this because you need to be focused. Okay. All right. So here's the issue with Ampere's law as it stands. I'm going to show you. So Maxwell fixed it based on the following similar or arguments like this. So here is a current I. Okay. And it's a long current. So Maxwell said, okay, what if I have a capacitor here? And then the current will continue. Okay. So as the current gets in, the capacitor will have more and more charge, right? This plate will get more and more charge. So the current goes on, and he said, let's apply Ampere's law to the following cases. Okay, so let's apply Ampere's law to the following cases. Okay. So we're going to apply Ampere's law right here, and we're going to choose our loop, like so. Our loop is going to be counterclockwise. And so, in what direction is the magnetic field if the current is to the right? Yeah, good. So the magnetic field will be in this circular direction. So B dot ds, so let me apply Ampere's law. I get this. B dot ds, closed surface is equal to U naught times I enclosed, right? Yeah, it's out of the board at the top, into the board at the top, yeah. And so it's like this. All right. So Ampere's law says B dot ds is equal to U naught times the current closed. The current that passes through the area. So imagine, here's the circle. Imagine it's like there is a soap bubble on it. So the current will pass through that. That's the area it's passing through. So that's fine. So here we have a magnetic field. The left side is B times 2 pi r, right? On the right side, I have U naught times I, and I'm good. We get a magnetic field. Okay. So here is what Maxwell said. Next, we're going to draw, it's the same loop, but now the area is no longer going to be flat. We're going to make the area into like the bubble coming out a little bit. So the area is going to do this. The area is going to curve out. Yeah. It's a three-dimensional area, yeah. So, is there a current passing through this area? Yes. So the right side is still good. Okay, the right side is still good. Hope you're following the argument. So when the area was flat, the current is passing through it. It's flat, so no problem. Now the area is curved, but there is still current passing through it. No problem. So the right side is still okay. Yeah.
Will we use a triple code?
No. It's actually a double integral.
Okay.
But we're not going to do any double integrals though. So next, all right. So far so good, right? So let's choose another area. Let's make it even bigger. Well, let's see. So let's make the area here. Okay, that's the area. Is there current passing through that?
No. Oh.
Yes.
Yeah.
Oh.
Yeah, the current is passing through it. Yeah, current. Here's the area ends here. There is current through it. So it's still good. Here is the issue.
Why you draw it that way?
Huh?
Why you draw it that way?
Why? Because we can. Because Ampere's law doesn't put any restriction on the area.
Okay.
So if it doesn't put any restriction, it should work for any area.
All right.
So the issue is this, though. If I draw my area here, how much current is passing through? Zero. So the right side is zero, but I still have a magnetic field. So how can that? Yeah, that's a problem. Okay. So how did he figure it? So he said, must be something missing. And that something missing goes as follows. When the current gets through, in this situation, that something missing should be 0. We should not know about it. But in the situation, if the area passes through this one, the purple area, that thing should appear. And this one will disappear, right? Because there is no current. So this is the area, right? So how did he fix it? He said, okay, let's look at the right side only, and then we'll add the term. And then at the end, this is theoretical. At the end, it becomes a law, and then it's verified experimentally. And when it becomes a law, it's a law. But we're just going through the arguments that led to that. So what he said is this: U naught times the current. The current is equal to the rate of change of the charge, right? So it's dq dt. The charge on the plate, the whole capacitor. But this is d dt. Q would be the surface charge density of the capacitor times the area of the capacitor, the plate area. So it's sigma times the area. Yes?
Wait, where do you get the sigma A?
Sigma is the charge on the plate, the charge per unit of area on the plate. So charge per area times area is Q. Next, we're going to divide by epsilon naught and multiply by epsilon naught. So I'm going to do this. Now, what is sigma over epsilon naught? Yeah, which field? Electric, yeah. So this is U naught epsilon naught d dt. Remember the electric field between the parallel plate capacitor is sigma over epsilon naught, right? So this is the electric field times the area. Now what is the electric field times the area? That's the electric flux. That's the electric flux. So this is U naught epsilon naught d electric flux. I'll put electric here because we get magnetic flux and we have electric flux. Okay. So now, let's see how this fixes the problem. How this fixes the problem. Ampere's law becomes this. B dot ds U naught I plus U naught epsilon naught d electric flux. Let's see how this actually fixes this problem. Okay. Let's go back to the very first surface, the one that was flat, this one. What's the current passing through the flat surface?
I.
It is I, good. What's the electric field through this surface? 0, there is no electric field outside of the capacitor. So this term is not there. How about here? What's the electric flux here? How much electric field passes through this surface? No electric field, yeah, 0. So this term still doesn't exist. Through this even bigger one, there is no electric field there, so that term is 0. However, in here, this term drops because there is no current. But this term would appear. And so we get this one. So this was the missing term. And this law became to be known as Ampere Maxwell's equation. Or law. Ampere Maxwell. So he fixed it by adding this term. Now these equations are complete. Okay, so 4 equations. Yeah.
Wait, so current is not driven by electric field. Current is moving not because electric field.
Which current?
Like any curve.
If there is resistance, you will need an electric field to drive the current. Yep. Ampere's law says V dot ds from the closed loop is equal to mu naught times the current through what?
So, are those loops?
Which one? So think of the loop. The loop is like the rim of a you know the thing you use to do a soap, make soap bubbles. Dip it in soap, and if you don't close on the area, you will have no this is the curve, and the area is just the area. It's the area of the soap bubble on it. The area of the circle. In that case, if it's flat, it is the area of the circle. On the now, if you blow on the bubble,
So
what happens?
we're talking about surface area of the.
Yeah. Yeah, this is, there is a surface area. I wish I can somehow, that's the area, okay? Yeah. Because it's zero, right? Electric field.
Oh, because it cancels out like
It
that.
cancels. We're assuming infinite. They're not infinite, but good approximation. Yeah. It's the ds is the you're going around the curve, so ds is the yes. It's ds is tangent to the yes.
For the purple area, why is the current 0 again?
How much current is passing here?
Well, there's no current
There is
there.
no current.
But how about the current that's like on
So
the?
it's zero. The current here is zero.
Yeah.
Yeah.
So what about the current on the
Here?
left side? No, the left side.
Here.
Like inside. Yeah, it's still inside that purple area.
Yeah, but it's not going through it.
Oh,
It's
like
not
it
passing
stops.
through it. Yeah.
It stops there and then.
Yeah,
there's
the current. Yeah.
Oh, okay.
Yeah. So what we're interested in is the current. Is there current that's getting through here?
No,
No.
that's it. Okay.
Yeah.
Why is the electric flux other than the purple one is 0?
Why is the electric? What's the electric field here?
Like inside of?
Here is a parallel plate capacitor. What's the electric field here? It's 0. Because the positive plate will produce electric field to the right.
Yeah.
The negative plate produces electric field to the.
Oh.
The two fields cancel. Yeah. And then inside the two fields, remember they're this way. So inside it's signal or epsilon naught. Outside is just 0. Okay, so the topics. So these are the equations. So let me pause this.